Professor Sheen from computer Harvard, who's going to talk about bootstrap and Ising theory.
Thank you very much. So I'd like to talk about some work we did earlier this year with Goodbye. There are a number of different motivations for this work. I would say that our goal is to, one of the goals is to get an analytic and also numerical handle on the non-perturbative physics, in particular non-perturbative resonances of a non-integrable strongly coupled quantum field theory. And there are very few, there is actually almost no examples of strongly coupled non-integrable quantum field theories where we can say a definitive way of non-perturbative resonances and non-perturbative regime of the S-matrix elements. And I would like to be able to say something about that, and I will discuss a somewhat general technique that we developed, and the application of that to a specific class of examples, which are these Ising field theories that we'll introduce in a moment. But let me give you also a kind of alternative, kind of philosophical motivation for this work. From the particle physics point of view, one of the common goals of particle physics is to you do some low energy experiments, and then you want to be able to predict, high energy physics or high energy resonances. And you can ask, is that even in principle possible? Because often our approach is to build some effective field theory, and then we match with some low energy data, and then we can kind of make some prediction. But it's often unclear whether these kind of predictions are, how rigorous are they? I mean, how much wiggle room do you have, or just, are you just making some guesses, or can you come up with some rigorous bounds based on your experimental data? So from the effective field theory point of view, let's say if you measure some scattering amplitude of your lightest particle, your theory, let's say it's some massive particle in some energy range, you can ask, to what extent can you probe or determine the property of high energy resonances? Now, you might say that this obviously seems to be, in some sense, impossible, because I can always imagine there's some high energy, very massive particle that are weakly coupled, very weakly coupled to a low energy particle. So let's say your high energy resonance has some mass that's much bigger than the mass of your lightest particle. And if the coupling is very weak, obviously the effect of this high energy resonance on low energy scattering will be arbitrarily small. But once you reach, if you do this scattering experiment, once you reach the energy to scattering, once you reach center mass energy that is very close in the vicinity of this high energy particle, you're going to have a strong resonance effect, some order 1 effect. This seems to already tell you that it's not possible to determine to some precision of the high energy resonances by doing low energy experiment. But that was a little too quick, because in the situation if the high energy particle is coupled very weakly to this low energy particle, its decay width is going to be very small. So it's true that if you have high energy resonance that's very narrow, then your chance of determining that by doing low energy experiments is very small. But if you restrict yourself to high energy resonances, let's say at some fixed higher energy, but with the decay width not too small, then there's a reasonable chance, at least there's no contradiction with the effective field theory reasoning, that you might be able to determine and possibly pin down the position of those resonances on the complex S-plane just by from low energy data. So I will show that this is actually possible in a very precise way in 2 dimensions. And I'll discuss the application of this idea to the Ising field. Yes.
So usually the mass of a high energy particle may come from totally different reasons. So you cannot determine the mass from low energy. Or there's
I'm going to tell you rigorous results. So this is just a motivation. I'm not saying where the mass comes from. I'm not. I'm just saying that suppose you have some effective field theory like this, can you determine the location of energy resonance from low energy data? But this is by no means a proof. I'm going to give a much more rigorous argument from an S matrix point of view. But the caveat is that I will only be able to give the argument in 2 dimensions.
I see. So I wonder whether there is a something assumption that is this high energy particle must be formed by the low energy excitation, not independently creating something.
Implicitly, yes. I'm only going to discuss resonances that show up as poles in the analytic intuition S matrix of the low energy particles. So I will be much more precise.
I see.
This is just kind of a broad motivation. Okay. Before getting to that, though, let me just explain what I mean by the Ising field theory in 2 dimensions, just to set up the subject of study. So this is going to be our, as I said, I'm going to describe a very general set of methods, but the main example I'm going to apply this to is the 2D Ising field theory. Since everybody knows what the Ising model is, you might suspect this theory is somewhat trivial, but the point of this is to explain why it is non-trivial. 2D Ising field theory. So if you start with Ising CFD, which in 2 dimensions, which everyone is familiar with, there are 2 relevant operators: the energy operator epsilon, the spin field sigma. Now I'm going to perturb the theory by turning on both relevant operators. So the coefficient of this energy operator, I call it MF, is going to be some fermion mass. And the coefficient of the spin field is conventionally called magnetic field. Doesn't matter what it is. I call it H. It's well known, of course, that if you only turn on energy operator, it goes to a free fermion theory, massive fermion. It's less well known what happens when you turn on the spin field. That's the thing I'm going to discuss. This generates Argand flow, and you end up with generically a massive quantum field theory. Of course, both MF and H are dimensionful coupling constants. Epsilon has more weight, 1/2 to 1/2. Sigma has more weight, 1/16 to 1/16. So you know that there is a dimensionless combination, which I write as MF over H, epsilon to the H15th. So this is a dimensionless coupling. Here, the sign of H does not matter because there's a Z2 symmetry under which sigma is on. But the sign of MF does matter because there is no Z2 symmetry under which epsilon is on. So you might wonder what happens if you have the sigma deformation. For either sign, you end up with a free massive fermion, but they're not quite the same theory because in one case, depending on the sign, you may be either infratrivial or you have a non-trivial Z2 topological field theory in infrared. And that makes a huge difference on the dynamics when you turn on this spin field. This massive quantum field theory is what we'll call the Ising field theory. That's the subject of study. And just to illustrate the extent to which this thing is non-trivial, so you can ask what is the spectrum of stable particles in the theory. They're all massive particles. So here's eta. Here's 0. So eta equals 0 corresponds to turning on only the spin field and no energy operator. That's turned out to be a special point. It's not obvious a priori why that's special, but it turned out to be special. In fact, from the kind of Landau-Ginzburg type of description, roughly speaking, if you think about thinking of this Ising as coming from tuning some phi-4 theory, then in this limit looks like phi-4 theory with some potential like this, and this limit looks like this double well shape, and this is in the middle. It's something like that. It doesn't look like anything special, but it turns out that there is something very special about e equals 0. As eta goes to infinity, as I said, this looks like 3 massive fermion. Eta goes to minus infinity. It turns out that once you go a little bit away from minus infinity, it's no longer it's far from a free massive fermion theory. This is in the confining phase. The spectrum of stable particles, there's a tower of mesons.
But it is also some massive fermion theory, just with negative sign. So I say this.
I will describe it from the point of view of the actual stable particles, and of course we can we will discuss. And at a certain point, eta equals 0. This is a point where the theory is integrable. This was famously solved by Numerical, and it's known to be equivalent to the affine E8 Toda theory at self-dual coupling. Anyway, never mind what that is. The point is that at this point it is integrable, and we can write the exact S matrix, but there's no particle production. There are actually 8 stable particles in the theory. So now, if I'm to plot the actual shape of the mass spectrum, let me normalize the mass according to the mass of the lattice particle, which I call M1. Note that this mass of the lattice particle is some non-trivial function of, say, MF and eta, or MF times some non-trivial function of eta. I will not write what it is. So in the units of the lattice particle, of course, the first particle is this over here, is 1. And generically, if there's no symmetry, anything that's more massive than twice the lattice particle will decay into the lattice particle. Can decay the lattice particle. So you only generically expect that any stable particle should be below the twice of the mass of the lattice particle. And that is indeed the case. So the second lattice particle has some mass that goes like this. There's a third lattice particle, this, and so on and so forth. So as you go to this negative eta regime, there are more and more massive particles, which is what I mean by this power of mesons. One can understand the property of their spectrum, but most of this picture is understood through numerics, that in a way I'll describe later in the video. And when the eta is bigger than a certain value, there's only one stable particle left. And then, of course, you might expect that as you tune this eta coupling, this will take resonances. Colloquially, one can say that the resonances are kind of bump in some scattering cross-section, and perhaps if the bump is very wide, you cannot define these things very precisely. But in fact, you can, because the resonances are posed in the analytic continuation, appropriate analytic continuation of S matrix elements, and you can say very precisely what they are, even if the resonances are wide. In fact, the wide resonances are going to be the subject of this talk. Just as a kind of another point of the broad motivation, the reason that one might, for pure theoretical point of view, one reason why one might be interested in wide resonances is this idea of nuclear democracy, the idea that perhaps sort of all different resonances and particles, stable or unstable particle theory, can be related by some kind of analytic configuration. It could be configuration angular momentum or some coupling or things like that. So we'd like to explore how these resonances behave as we vary the parameters of the theory.
Excuse me.
Yeah.
So since Ising model likes like Marana fermion theory, and this energy term like a Marana fermion mass term, right? So when you have a very negative mass, I just wonder why the negative mass and the positive mass spectrum so different.
Well, that's an easy way to. I mean, first of all, there are different theories. It essentially has to do with how this sigma behaves very differently in the two theories. Well, one intuitive way to understand this from the Ginsberg picture is just that, over here, it looks like in the 5-4 theory, like description, it looks like in the double bubble, but with the slight, with the degeneracy slightly lifted. So the fermions are supposed to be kinks. So that's what the fermions are. But as you see, this kinks will have to be confined because on one side there's going to be some non-zero energy density, so it's going to diverge, unless there's an anti-kink.
I see.
So these mesons are the kink anti-kink bound states.
Okay.
Okay. So the approach we're going to so the question we're going to be interested in is not just the spectrum of stable particles. These are understood using Hamiltonian truncation methods, but the property of resonances. so the method is two parts. So first we'll get elastic scattering data from Hamiltonian truncation. And in this case, we'll use a specialized method of Hamiltonian truncation known as the truncated free fermion space approach due to Europe and some logical. So this is kind of old technology, even though we're applying to compute some new quantities. But then we'll bootstrap the S matrix beyond the physical elastic scattering from the elastic data. So I think I'll spend most of the time to describe this the second strategy. Then I will describe some results and show some slides at the end. But let me now go back and talk about the properties of sort of the simplest non-trivial S matrix element, which is the 2-to-2 scattering of lattice particle. So we'll consider, let's say, 2-to-2 scattering of the lattice particle in our theory. So the mass m is going to be our m1, and measure there. As usual, you can define these STU minus m variables. But in 2 dimensions, for the scattering of identical particles, u is just identically 0. Because it's sort of the difference between these two momenta squared. And so in 2D, and t is just 4m squared minus s. So the kinematics of 2-to-2 scattering in 2 dimensions is simple. This is this had, of course, had nothing to do with integrability. This is for any 2D quantum field theory. And I would say that in some sense, you should think of this 2-to-2 scattering amplitude as analog of a single particle wave amplitude in higher dimensions. But the crossing, the point is that in 2D, the huge simplification is the crossing symmetry is very simple. It relates this particle wave to itself as opposed to in, say, 4D, where it will mix all the particle waves, which would be substantially more complicated. As usual, one introduces this rapidity variable, theta, in related to center mass energy squared s in this way. The theta is the rapidity. And now, as usual, it's important to study the analytic property of the scattering amplitude on the entire complex S-plane and possibly beyond.
What is T and S? Is that the total mass, total energy in one channel?
So if in the convention where momenta are all going in, let's say, then S is minus U1 plus B2 squared, and T is minus G2 plus B3 squared. With understanding of appropriate analytic configuration, they're supposed to be related by crossing that exchanges S channel with T channel. Okay, so let me introduce, let me discuss the parameterization a little bit. So there's the S plane, and then there's also the theta plane, where I draw the, okay, so in my parameterization here, the physical regime, which corresponds to S greater than 4m. So let's say the real axis, this is 4m squared. S is greater than 4m squared. As usual, there's a branch cut. And along this cut is basically mapped to the real line in the theta plane. Due to the crossing relation, there's going to be, I'll describe this in more detail in a moment. There's a corresponding T-channel cut, represented as S-channel cut that goes from minus infinity to 0. Okay, so under this map, the entire complex S-plane, which is usually in this context referred to as the quote-unquote first sheet of the S-plane, referring to the fact that there's going to be some nice analytic property on the entire complex S-plane. We can also try to ask what happens if we can continue through the branch cut to the second sheet. So that'll play a role in a moment, but refer to this S-plane as first sheet. So the first sheet is mapped to the strip on theta plane, which is between imaginary part of theta between 0 and pi. Okay. So let me colors.
There's a very basic question.
Yeah.
I'm just wondering, say, if we label this particle state by like S and T channel using momentums, does it always assume the theory has a excitation as a free particle description labeled by momentum?
No. Well, they're not free particles. You see, we're going to be talking about strongly coupled interacting fully invariant quantum field. But as usual, the definition of S matrix is based on the idea that when the particles are far separated, they're supposed to be weakly interacting. So if that's not the case, the S matrix element is not supposed to exist. Okay, so this will be the case because we're talking about some massive quantum field theory, and in this particular theory, we expect that when the particles are far separated, they behave like free particles. So you can define in and out states, and you can parameterize your basis of your Hilbert space in terms of in and out states. The parameterization is as if they were free particles, but of course they're not actually free particles. I mean, it's just a label. And as usual, the Hilbert space, the set of in states are complete basis of your Hilbert space. The set of out states are complete basis of your Hilbert space. And the unitary transform between the in and out space is S matrix.
So the M is a P1 square, right? So every particle has the same mass.
Yeah, minus P1 squared. So Pi squared is minus M squared. That's right.
And also, this branch cut is some scattering amplitude have this structure.
Yeah. Of course. In fact, I haven't said what I'm continuing. So the statement is that the canonical part of the S matrix element, after you strip off the delta function, is going to be the limit of some analytic function that approaches this physical cut from above. So I'm going to write that in a moment, but I was just trying to map out the kinematics for the moment. Okay, so for some reason, I'm going to talk a lot about the right half of the S-plane, just to orient ourselves. It's going to map to this lower half of this strip. Then there's going to be some special point on the physical cut. Let's say over here. I'll call this the inelastic threshold, IT for short. So if there are no other particles, stable particles, then the inelastic threshold will be 9m squared. It's when you can produce 3 particles. That's when you can have particle production. Now if you have another type of, particle that's slightly more massive than m1, the inelastic threshold could be m1 plus m2 squared, for instance. So there's some inelastic threshold somewhere, and there's some further complicated branch cut structure over there. It turns out if you unfold to this theta plane, then this cut in this elastic part goes away, and you just have a cut starting from the inelastic threshold, which is mapped to somewhere here on the plane. There will be some other cut over there, which will be related. And there'll be some other cuts that are related by crossing. So I'll describe all these relations more precisely in a moment. I just want to put this in on the picture. Now, as I just mentioned, the scattering amplitude is going to be analytic continuation. There's going to be an analytic function that has some analytic property on this complex S-plane, and its limit, as it approaches the cut from one side, is going to be the physical scattering amplitude. Now we're going to be focusing on this entire analytic function, and this function is going to famously have some poles, which are associated with stable particles. And so there's a pole over here, which is m squared, for example, if the particle has self-coupling. So this is the self-coupling pole. This corresponds to the process where through scattering they exchange the particle itself. And if you have some other mass of particle, some mass m2, there'll be some other self-coupling pole. Other pole due to the other stable particle. And in 2D, there's a special, due to the special kinematics, there's a corresponding T-channel pole due to self-coupling, like that, that corresponds to the pole in the S-plane at 3n squared. Okay. Now, so those two are mapped to, as I said, the theta along the entire real axis is in the physical regime. So these self-coupling poles would be somewhere over here. These are self-coupling poles. Now, it's sometimes it's colloquially often said that if you have resonances, they'll also be supposed to be seen as poles on the complex S-plane. But in fact, they do not appear on the first sheet. So if you start over here and then continue, you will not see any pole that correspond to unstable particles. So unstable particles or resonances correspond to poles on the second sheet. So there will be some. So if you can continue through this cut, you have some pole over here, which will turn out to be related to a zero on the first sheet for a reason that I will describe in a moment. So the claim is that the resonance will be reflected zeros on the first sheet and poles on the second sheet. In higher dimensional analog, say 4 dimensions, this statement applies to partial wave amplitudes, not to the full 2 amplitude. So the resonances will be of some given spin will be seen as a zero of that corresponding partial wave amplitude on the first sheet. And it will correspond to some, you can have some resonances anywhere sort of over here, and they'll have the coming pairs because of crossing. Okay. On the theta plane, you can, if you continue to a second sheet, in fact, on the theta plane corresponds to any continuation from here to because it's square, so if you continue sort of across this, the theta plane corresponds to continue to across this cut. So this is not, which is not a cut on theta plane, but it's what corresponds to the elastic part of the physical cut. And the second sheet is mapped to this strip down here. So this is the first sheet, and this is the second sheet. As I'll say in a moment, all these subcutting poles will be related to zeros on second sheet, and these zeros will be related to poles on the second sheet. Okay, and for the convenience of discussion, I will have to introduce one more parameterization, which is a parameter called z. In this parameterization, I'm going to map this half of the S-plane, this green strip of green half of the S-plane, onto the unit disk. So far, this is just some arbitrary parameterization, but its use will become clear in a moment. So let me write the formula. So z is defined to be sinh of theta minus square root 3 over 2i, something like this, which can be written in terms of s in this way. As I said, the job of this z is to map this entire the half of S-plane to its unit z disk, such that the self-coupling pole over here is going to be mapped to the origin z equals 0. And if you have some other physical stable particle, there will be other poles somewhere along the real z-axis. The way I define this map is such that the elastic threshold s equals 4m squared is mapped to z equals -1. And the infinite energy limit corresponds to z equals +1. And the inelastic threshold will be turn out to be somewhere here. Or you might think that this is the energy not far about two particles, but actually this parameterization is somewhere over here, which is a good thing for my numerical purpose. And this inelastic cut is mapped to the thing on the boundary that connects inelastic potential to infinity. So in this parameterization, the physical cut gets mapped to the boundary of this disk, and the bulk of the disk corresponds to this half, the right half of this. Okay. So that's just parameterization. Now let me discuss the physical properties of the physical S matrix. The physical S matrix element should be thought of as there's some function I call S of little s, which is this S center mass energy squared, that has the property that I described. Now, take this function. If you take S be real from m squared to infinity, and then you take the limit where you approach so if you take the limit, you approach from above, you get the physical S matrix. That's what I said earlier. This is supposed to obey a number of properties. So unitarity, and at a very simple level of 2 to a scattering, would say that this absolute value is bounded by 1 for S along this physical cut. That's just because if you scatter 2 particles, the probability has to be is either equal to 1, in the elastic region where it could be slightly less than 1. In the inelastic region, there's some probability of scattering into other final states, other out states. Now, what I just said, the elastic unitarity amounts to a statement that this S matrix element, its modulus, is actually equal to 1 for S, let's say, between real S between 4m squared and the inelastic threshold squared. There's going to be real analyticity, which asserts that this function is, we take, evaluate its the conjugate of the S variable and then conjugate again, you get back to itself. Just saying that, say if you imagine if you can Taylor expand it, then its coefficients are supposed to be real. Crossing is a statement that S, you can exchange S and T. With the understanding that we're talking about the actual analytic function, because otherwise you may worry whether you're going from the physical regime to outside the physical regime. So with the understanding of this analytic property, the crossing will make sense. Now, in terms of theta, it will turn out that if the operation of sending S to S star corresponds to sending theta to minus theta star, this real analyticity corresponds to the property that S of theta is equal to S of minus theta star, and the crossing corresponds to the statement that S of theta is S of pi I minus theta. So here I'm using the same notation for function of S and function of theta, hopefully there's no confusion. In particular, this elastic unitarity implies that, let's say along here, over here, elastic unitarity implies that S theta times S theta star, times S of theta star is equal to 1 over here. But if I'm along this real value of theta, then theta star, of course, is the same. But now the point is that this object here, which is actually equal by the analyticity equal to S of minus theta, is also an analytic function in theta. So if S theta times S minus theta is equal to 1, along this real segment has to be equal to 1 everywhere, going to continue. But if the theta is on the first sheet, the theta is minus theta is on the second sheet, which is why the poles and zeros come in pairs on the first sheet and the second sheet. Okay. It's important to also know some property of S matrix at infinity when constrain the function, this analytic function. So let me erase this picture now. Under some general axioms upon the field theory, one can prove certain boundedness property of the S matrix elements. And I'm going to assume that for now. So the boundedness of S near S equals infinity will tell us that you can write this S of theta in the following form, which would be quite useful for the following discussion. So there's going to be I can separate this S matrix element into a purely elastic piece, which I call the CDD, sometimes called the CDD factor, and another factor that captures only the inelastic probability or inelastic cross section. So it takes the following form: e to the minus integral theta prime over I log of f theta prime over sinh theta minus theta prime plus I epsilon, where f of theta here defined for real theta is just the 2 to 2 scattering cross section. So that is in my notation here, limit of epsilon goes to 0 of s of theta plus I epsilon s of theta plus I epsilon. So this is the cross section. It's a real function with value between 0 and 1 in general for real theta. I only define it for real theta. So the way you can read this is that if f theta equal to 1, it means that the scattering is purely elastic. This term just vanishes. This thing just vanishes. So this thing just captures the some kind of contribution from particle production or inelastic process. These SCDD, on the other hand, this guy, SCDD, is meromorphic on the physical strip, which is the first sheet over here, and it's crossing invariant, so a base crossing, because the second thing by construction of base crossing. And that is purely elastic, so that this thing is a pure base for real theta. Now, if you make the further assumption that there's no essential singularity at infinity, you will be able to write this as some product of zeros and poles, but that assumption would not be essential for my purpose. Okay.
What does that assumption mean physically?
Physically, you in fact, I think it's kind of a lore that one expects a low quantum field theory to have that property. For a theory with gravity, you expect that to fail. But I'm not aware of a proof of either statements. All right. Now, describe this. So actually, for the subsequent discussion, I'm mostly going to think in terms of this z-disk, which will be kind of convenient for my purpose. You see, we said that there can be some other physical pole, maybe some other. So it's a self-coupling pole. There's some other stable particle. Will be over here. And we said that if you have some resonances, you can have some zeros over here, for example, if they have narrow width, or they could also be over here, in which case they don't have to come in pairs. So these are the kind of resonances, unstable particles. They'll be zeros. our strategy is going to be the following. So on this part of the arc, where the scattering is elastic, I'll refer to this part as the elastic arc, and this part we refer to as the inelastic arc. I'll call it curly J, inelastic arc. And our strategy is going to be the following. We like to understand the property of these resonances. And we need to have some input. So far what I described works for any 2D massive quantum field theory, and just some of the estimated of the lightest particle. So you can already put some interesting kind of universal constraints, but that is not my goal here. What I would like to do is to take some input that's specific to this Ising field theory and make the predictions about the position of resonances in Ising field theory. And the input is going to be some data, numerical data in fact, about the scattering phase in this long elastic arc. I'll describe the method for doing that. And then we're going to numerically continue into the bulk of the disk. Now, of course, you might say that that's kind of impossible. Numerical continuation, the error is going to be huge. But the key points of the game is that we know this analytic property of the S matrix. We'll know the location of the poles because those locations which are bound to stable, massive stable particles can also extract numerically. So I know the location of where the possible poles are. I don't know where the zeros are. I don't know where the residues of the poles are. But I know the position of the poles. So I know the position of the poles. I would have up to some error, I will know the S matrix elements along the elastic arc. Actually, along any segments along the elastic arc would be sufficient for my purpose. The more you know, the better it will turn out. And I know that it's bounded by 1 along the inelastic cut, so or inelastic arc. So I don't know a priori anything about the value of the S matrix elements along this inelastic arc, but I know it's bounded by 1. And that will turn out to be enough for me to do this numerical continuation. So the upshot is that I will be able to prove a lemma in complex analysis, which, by the way, I don't know if it's a new lemma in complex analysis, which I highly doubt since it's a subject that has been developed for hundreds of years. But for our purpose, it's convenient to use this lemma, which will tell you that if it's bounded in some uniform way along the boundary of the disk, you know where the poles are, and if you know its value along some arc to some accuracy, then you can put a rigorous bound on this function in the theory in the sense that if you give me any ansatz so I have some physical estimated element. Suppose I know its value near the boundary, near this on this elastic arc. If you give me any function that approximates this sufficiently well along the known part, the elastic part of the arc, then I can find the error everywhere in the interior. And if you make a small mistake, if your error is very small along the boundary, the error is going to be very small at any given point in the bulk as well. Now that bound is not going to be uniform. It's going to be worse when you're approaching this region, but it's going to be good in the interior of the system. I mean, this is consistent with the effective field theory idea that I described at the beginning, that if you have some very narrow resonance, which will be like way over here, the chance of you determining that is very small. But if you have some wide resonance over here, then you can pin it down given this elastic data. So let me assert this lemma just to put us on firm grounds. And then I will probably just show some pictures. So lemma is the following. So let's say f of z. Just think of this as an error, not the S-matrix element itself that we're trying to find. So suppose f of z is analytic and bounded on the interior. Bounded in the interior of the disk and continuous near, or let's say along the boundary of the disk. So this condition I'm setting it just for simplicity of the statement. You can, this continuity can be relaxed. In fact, I don't really require it. All I meant to say is that this error function, it's some function, if you approach the boundary from the interior, it's supposed to behave in a continuous way. That's all I meant to say. And given this division, the choice of this arc curly I and this complement curly J, exactly where the arc is not important. They don't have to be connected or anything like that. Then for any Z inside the interior of the disk, I'll be able to bound this error function in terms of some quantity that depends on its value along the boundary in the following way. The actual detailed form of the bound will be useful for me, so let me write it down. So there's some function B called BZ that I'll describe in a moment. 1 minus 1 over 2 pi times the length of this curly I, but transformed in a certain way. This tau Z is a mobile transformation that I'll describe in a second, times the exponential of the integral along this tau Z. I'll describe all these things in a second. du, I just want to write it down to be definite. Log of f of tau Z of u, this value, where the various quantities are, the theory here are the following. So tau Z of w, so tau Z is a map from the unit disk to itself. It takes the form of a Mobius transformation. I will not write the explicit form, it's not very interesting to write it down. It maps 0 to Z, which is of your choice. And here what I need to use is, so over here I have this I and J, and if you do this Mobius transformation, they get mapped to some different arcs. So let's say this is tau Z inverse of J, and this is tau Z inverse of I. So the inverse of this I and the Mobius transformation, that's the domain of integration over here, and this is just the length of that arc. And finally, so this is log of the absolute value of this function, basically on the elastic part of arc. So this f is meant to be the error. So if the error is very small, this is going to be hugely negative, and this whole thing will be suppressed. So you can see that this is going to be quite a strong constraint. And BZ, so what is BZ? BZ is basically the average of this function on the inelastic part. J, let's see first. Now, of course, I'm not going to be able to know what the error actually is on inelastic part. But the thing is, I'm going to know that it's bounded by 2 because each function, the function and the ansatz I'm going to use to approximate it, both are bounded by 1. So the error is bounded by 2. And so this BZ is bounded by 2. That's all I need to know to apply this formula. Okay, so this thing one can prove without too much effort. I won't really have time to describe the proof of this. It's like a one-page proof in our appendix. So the way we're going to use this is that, you see, if you, so what I'm going to do is I take the S of Z, now think of the S matrix as function of Z up to these poles. So I'm going to strip off the poles in a way that preserves all this, well, I should say divide by this CDD pole factor. So that I get something that have this pole stripped off and it still have the same analytic property on the, it's bounded by 1 and boundary and so forth. This I'll call this the function G of Z. And then I'm going to consider a ansatz or approximation called G tilde of Z, which is some analytic function I can construct, and I fit the data of G of Z on this elastic arc any way you want, any favorite fitting you want, and will justify the error a posteriori. So the error function is going to be the difference between G of Z and say G tilde of Z. So if I look at the G tilde, let's say I discover that there's some range where G tilde of Z is non-zero, and if I know that the error is less than the f value of G tilde, then of course I can then rigorously rule out the possibility that GZ will be 0. So I will know that GZ is, I know that in this region there cannot be any resonance. Now, so this will turn out to nail down some islands of possible resonances. And if I can, where this error bound is not less than this value of G tilde Z, and if I can determine in a definite way the existence of resonance in this small island, if you measure the phase of G tilde Z around it. And in fact, in our practical application, this island will be very tiny, and you can pin down the resonance very accurately. But then there will be some other domain over here where you cannot bound the error, which is to be expected. So let me now show you some plots. I don't have time to discuss how we actually extract elastic data, which is will take like half an hour to discuss. I will not have time to discuss that. But it's that part is old technology of Hamiltonian truncation. So the way we're going to extract elastic data is basically to truncate you start with the free massive fermion theory, and it turns out that one knows all the matrix elements of the spin field sigma between free fermion states. And there's some complicated formula which I won't have time to describe in detail, but it's a known formula derived by Analytic for the matrix element of the spin field in the free massive fermion theory on the finite circle. So everything here, there are complicated functions involved, but they're all known exactly. And you just truncate the Hilbert space truncate the Fock space of free massive fermion theory, and you add this perturbation, and you diagonalize the Hamiltonian matrix. This turns out to converge kind of empirically in a power law fashion with the increasing truncation level. So there's some small error that you have to take care of, but given enough computation power, you can get reasonably good numerical results for the energy levels of this system on the cylinder or on the circle in this theory.
Excuse me. Let me try to understand. So when eta is very negative, then the spectrum, as you said, is this resonance of this bounded domain.
Yeah. So this is the actual data. So I'm showing you this. These are not resonances. These are the stable particles.
Yeah, stable particle. I mean.
Yeah.
But those particles, so the spectrum over there seems can be obtained quite accurately because you have a string tension from string tension solving this mode.
So there are many ways you can imagine to compute this. Here I'm telling you one way to get this numerically, and it actually works uniformly well for any value of theta. It doesn't matter whether it's positive or negative. You can just check numerically that it converges.
I see. So it's not like using the negative eta result to
No, I'm not using that at all. There's no perturbation theory involved. I should say that it's possible to study this system using perturbation theory, but it's a bit non-standard. It's not like Feynman diagrams because, say in the free fermion theory, this sigma spin field, cannot be expressed in terms of fundamental fields in a simple way. And if you want to do perturbation theory, you have to do form factor perturbation theory, which is actually quite hard. Even the leading water computation is extremely difficult, but that has been done by Analytic, and nobody has ever computed beyond the leading water. But I don't need any of that. This is just diagonalizing the Hamiltonian. And this turned out to work nicely even for eta equals 0, or near 0, where the coefficient of deformation is actually huge. But it turned out to work quite well even in that regime. So over here you see that there's some two-particle states. So before in the work of Zamolodchikov, he was interested in getting some data about the one particle states and make some educated guess about the dynamics. But here, we want to directly extract the data of two particle states, which you might, I think that's quite messy. But then, using the Bohr-Sommerfeld kind of quantization relation, you can extract the scattering phase in the elastic regime out of the spectrum of two particle states. So unfortunately, I don't have the time to describe that procedure in detail. I'll just show you what the kind of data, what kind of result looks like. Here, what you do is you collect the data of, say, the first two particle state, the second two particle state, third two particle state, fourth two particle state, fifth two particle state, and so on and so forth. You translate that into what would be a prediction for the scattering phase using the Bohr-Sommerfeld quantization formula. Now, the Bohr-Sommerfeld quantization may not be exact, but it's only not exact because of kind of rapid interaction. So if the range of interaction is small compared to the radius, the correction to that quantitative relation will be exponentially suppressed, which is the key to applying this. And then you can vary the radius, and if you vary the radius, then each level will change. So this is in this plot. I'm collecting data for the first 5 two particle states, but for varying radius. So as you vary the radius, you see that sometimes they overlap, sometimes they don't overlap. When they don't overlap, it's because of these finite size effects. But if you have the finite size effect, they're kind of in your face. You can just throw it away. I'm just going to drop this piece. And over here, you see that the most overlap except for this finite size effect, which you can just drop. And that will be sufficient for this purpose because I don't actually need strictly all the elastic scattered data on the entire elastic arc. For a part of it, that will be sufficient for my purpose. And I compute the error a posteriori after I come up with some approximation. So this is just some sample results of the elastic data after you discard the small radii cases where the finite size effects spoils the result. So this horizontal axis is basically some transition of energy, and this vertical axis is the elastic scattering phase. So this is from Hamilton truncation, and now we do this numerical continuation. Here's what it looks like. So this is the plot, supposed to be the plot of the z-disk. This first colored plot is the absolute value of S of z, and this red dot is a pole, and the blue dot is a 0. So the pole position I already know, so that's not something new, that's already from the numerics, but the 0 is the position is something that I cannot get directly from the numerics. That's part of the prediction here. But then there's some resonances that are very close to the 0 is very close to the boundary that you cannot actually see in this first plot. In the second plot, I label by these crosses that you can see. And some of the crosses are buried in this ocean of this blue stuff where you cannot say for sure whether the resonances are there, but some of these are definite. So they are in these tiny islands. It turns out that one of these resonances is in a tiny island by itself near the boundary.
Shouldn't we be seeing more poles?
More poles?
Yeah. Two stable particles.
Sorry. I think sorry. Okay, so first I should say that in the second plot, I'm not plotting the poles at all. In the first plot, it turns out that I think in this situation, there are two poles that are almost on top of each other. So you don't see this in the picture. And actually, if we're close to 0, there's a third pole.
Right.
But I didn't plot. We have more plots in the paper. But it turns out that if you vary eta, this pole kind of moves out and gets replaced by a 0 that comes back in. So, but the 0 is actually what happened to the pole. So that's the idea that this M3 has turned into a resonance, which is precisely it. Okay, so just to, I think this is the last slide, I think. This just to demonstrate you can also compare this result from actual very hard calculation from perturbation theory at leading order. This is, I won't really explain what these are, but this is in the weak couple fermion phase for sufficiently large eta. And there's some data that kind of agrees with what we get here. And around eta equals 0, you can compare with form factor perturbation theory around this E8 integrable theory. And that's actually quite hard because the form factors are very, very complicated. These have been solved by these have been solved in the past, and there have been computations of the energy and the width of this M4, the fourth lattice particle, which will change to a resonance as you move away from the infinitesimally away from the integral point. So that's this dotted lines here. Our actual data from this numerical calculation are these colored crosses. And you see that it can qualitatively even agree at the level of the width of the resonance. So that's a kind of demonstration that at least we're on the right track here. So I should stop here, and I should say that I described some very general method that can qualitatively generalize in various ways. You can consider extended to maybe massless particles or higher dimensions, but there are various difficulties in each possible generalization. So I'll stop.
I try to understand what is the input. You said that to get S a vector element, you know the position of pole from your marks, but you don't know the zero. So do you assume zero to be somewhere?
No, I don't mean to assume that at all. So when I know the poles, but importantly, I also know this elastic data, so which is this. So what this is plotting is the value of the S matrix along this elastic cards. Elastic cards, so like along there. So I know the scattered phase to some approximation along here, and I know the position of the zeros.
So when you say you know, means there's some numerical calculation.
That's right. That's this Hamiltonian truncation. So the numerical calculation, which I didn't really have time to describe in detail, is I take the free Fermion Hamiltonian, which of course I know I write in Fock space basis. So there's some infinite dimensional matrix.
Yeah.
I truncate that infinite matrix to finite matrix with some large truncation level, like say 5,000 states included, or even more, let's say 10,000 states. And then I will deform this Hamiltonian by the spin field. Right? So that's Ising field theory. And I know the matrix element of the spin field. Here it is. Sigma, the matrix element between the Fock space states, are given by this formula. So there's some function I didn't tell you what they are. They're complicated but known functions. So everything can be plugged into the computer, you put on the cluster, and you diagonalize.
I see.
And this is the result of the diagonalization. And from these two particle states, I extract that elastic scattered phase. And I feed this into the numerical annotation. That's the procedure.
One more quick question.
You mentioned that there's a limitation only for 2D space-time, not for high dimension. Is that a reason just because we don't have an equivalent tools like complex analysis?
I mean, you still have complex analysis, but just the analytic property of these functions are more complicated. I guess I erased the picture of this S-channel cut and T-channel cut. So you see, the key point is that the 2D S matrix is like the single partial wave. So the S-channel cut and T-channel cut are directly related by crossing, and I can bounce both of them, the value by 1 on both cuts. So that's essentially the reason that I was able to map this to the disk, which I've already implicitly used the crossing. So I'm only in the half estimate. Now, in the higher dimensional story, the crossing works in a much more complicated way at the level of the partial waves. The crossing, roughly speaking, is exchange S with T, but the partial wave expansion, in the S channel, is such that so each partial wave is going to be a function of only one variable, say S, but the crossing now mixes all the entire infinite set of partial waves. So for each partial wave, along S channel cut is still bounded by 1 by unitarity. But along the T channel cut, it's supposed to be constrained by unitarity in some way. But it's very hard to say exactly what the constraint is because the crossing kind of related to all the other partial waves in a quite complicated way. So there are a few substantial technical obstacles that one has to overcome. I don't have time to describe them, but it's a substantial. It will be a very non-trivial extension of what I'm doing here. And in fact, I'm not sure that the analog of the lemma I'm describing here can be actually extended to higher dimensions. It might be possible, but I mean philosophically, it should be possible. Otherwise, the goal of particle physics, can never be achieved because you think that when you run data, there must be a way to pin down these resonances. But in practice, how to do this using analyticity and unitarity of S matrix is yet to be understood.
Let's take the speaker again.